Have you ever stopped to wonder how the digital world actually works? I mean, how can websites and apps handle thousands or even millions of people all clicking, buying, and posting at the very same time without just collapsing into total chaos? Well, we're about to pull back the curtain on the invisible force that makes it all possible: concurrency control.
So, let's set the scene. Your favorite artist, they just announced a tour. You and 1,000 other superfans are poised, finger on the button, the second those tickets go on sale. You all click buy at the exact same millisecond for the very last ticket. So, what happens? Who gets it? Does the whole system just crash? Does it accidentally sell the same ticket 500 times? This right here is the core problem that concurrency control was born to solve.
And this isn't just some hypothetical question for fun. It is a fundamental make or break challenge for any system that uses a database. Which, let's be real, is pretty much everything online. It's what we call the concurrency problem. How do you manage all these simultaneous operations so they don't step on each other's toes and corrupt the data?
And this slide really lays it out in black and white. Without concurrency control, it's just the Wild West. You get double bookings, data that mysteriously vanishes, and constant system crashes. It's absolute chaos. But with the right controls in place, you get orderly operations, data that you can actually trust, and correct, consistent results every single time. We have to have a way to protect our data from these kinds of inconsistent changes.
So how do databases manage to bring order to all this chaos? Well, they use a concept that is both beautifully simple and incredibly powerful: the transaction.
Think of a transaction as a package of work with one simple, unbreakable rule. It is all or nothing. A great example is transferring money. That single transfer involves two distinct operations: taking money out of your account and putting it into the other person's account. Now, imagine if the debit from your account works but the credit fails. You've just lost money into thin air. A transaction ensures that either both operations happen or neither of them do, which keeps the database in a perfect, consistent state. Okay, so we have these all-or-nothing transactions. That's a great start, but how does the system stop two transactions from tripping over each other while they're actually running? The number one tool in the database's toolkit is a mechanism called locking. And this is the perfect analogy. The database management system, the DBMS, is basically a traffic cop at a super busy intersection. It doesn't just let everyone drive through at once. Instead, it uses a system of locks to direct the flow, telling transactions when they can go and when they have to wait, making sure nobody collides.
Now, just like traffic lights, there are different kinds of locks. The two big ones are shared and exclusive. A shared lock, or an S-lock, is for reading. It's pretty chill. Multiple transactions can all read the same piece of data at the same time, no problem. But an exclusive lock, an X-lock, that's for changing things, modifying data. And this one is strict. Only one transaction can hold it at a time, period.
Okay, let's actually see this in action. Here we have transaction T1. Its job is to change an account balance, which means it needs to perform a write operation. So what's its first move? Before it can even think about touching that data, T1 asks the database's lock manager for an exclusive lock. And since nobody else is using that data right now, the request is granted. That account is now completely locked down for T1's use only. But wait, here comes another transaction, T2. It doesn't want to change anything, it just wants to read the balance. So to do this safely, it politely asks for a shared lock on that very same account. And the request is denied. Why? Because T1's exclusive lock trumps everything. It blocks everyone else out, readers and other writers. So T2 is put into a waiting line. It has to sit there patiently until T1 finishes what it's doing and releases the lock. This is crucial because it stops T2 from reading some weird, half-updated, inconsistent number.
Now, just having locks isn't quite enough. You need rules of the road for how to use them. Otherwise, you can still cause all sorts of problems. The most common set of rules for this is called the two-phase locking protocol, or just 2PL.
Specifically, most databases use a super disciplined version called strict two-phase locking. Here's how it works. First, you have the growing phase. In this phase, a transaction can only acquire locks. It goes around and gathers up all the locks it's going to need. It cannot release a single one. Then, once the transaction is completely done with its work, it enters the shrinking phase, where it releases all of its locks at the same time. This strict rule is what guarantees transactions behave properly, preventing weird data issues. The trade-off, of course, is that all this locking and waiting can sometimes slow things down.
But this very disciplined approach can lead to its own unique, tricky situation. What happens when two transactions are each politely waiting for the other one to finish first? You get a standoff. And in the database world, we call this a deadlock.
Let's go right back to our ticket buying scenario. Transaction A swoops in and successfully gets an exclusive lock on the seat record you want to buy. Awesome. Its very next step is to lock your payment record so it can process the charge.
But at the exact same instant, another process, let's call it transaction B, maybe it's processing a refund, it locks that very same payment record. And what does it need next? Oh, you guessed it, the seat record that transaction A is currently holding.
And there you have it. A is waiting for B, and B is waiting for A. Neither of them can move forward because each one is holding something the other one needs. They are stuck in a circle, waiting forever. This is a deadlock, and it will freeze these transactions solid if nothing is done about it.
So how does the system break the stalemate? Well, the DBMS is always watching for these situations. It builds a kind of map called a waits for graph that shows which transactions are waiting for which other transactions. When it sees a closed loop in this map, A waits for B and B waits for A, it knows it's got a deadlock on its hands.
Once that deadlock is detected, the database has to act. It becomes a reluctant referee and has to choose a victim. It picks one of the deadlocked transactions and just aborts it. It rolls back any changes that transaction made and forces it to release all of its locks. This breaks the cycle, and it allows the other transaction to finally move forward. And usually, that aborted transaction just gets restarted automatically. All right, so after all this talk of locks and phases and deadlocks, let's take a step back and look at the big picture. Why is this stuff so incredibly important?
It's important because concurrency control is the silent, invisible engine that powers our entire digital lives. Every single time you transfer money, add something to your shopping cart, book a flight, or even just see your social media feed update correctly, you are witnessing successful concurrency control in action. Without it, none of these systems could even begin to function reliably.
So the next time you use an app or a website and everything just works, remember that unseen traffic cop inside the database, meticulously managing all the transactions and locks to create that seamless experience for you. The internet feels so instant and infinite, but it's really built on a foundation of these incredible invisible rules. It makes you wonder, right? What other hidden mechanisms are out there, working tirelessly to make our digital world possible?